You've just fine-tuned a high-performing 32 billion parameter language model for your product search engine. It's domain-specific, it's accurate, it's ready. You hit deploy and you see the dreaded OOM error, CUDA out of memory. On your shiny L4 GPU with 24 gigabytes of memory, the model simply does not fit. This isn't just your problem. This is the new normal. Whether you're training foundation models from scratch, fine-tuning adapters using PEFT, or deploying LLMs in real-time chat, search, or summarization, GPU memory is now the most precious and most constrained resource in our ML stack. In just a few years, we've gone from GPT-2 at 1.5 billion parameters to GPT-3 at 175 billion parameters. And now, OpenAI's next generation model is rumored to be more than 1 trillion parameters. These power products you use every day, such as ChatGPT. But here's the kicker. While model sizes have grown by orders of magnitude, GPU memory simply hasn't. Even the state-of-the-art H100 GPU only has 80 gigabytes of memory. What does this mean? We can't simply scale the model size using a single GPU. Instead, we have to rethink how we organize computation across multiple GPU devices. And that leads us to today's session. Hi everyone, I'm Goutham Ramakrishnan, applied scientist at Amazon, and welcome to this NIIT masterclass on scaling large language models with model parallelism. In this session, we are going to unpack one of the most important problems in training and deploying large models, that is GPU memory. It's not just about VRAM specifications on a sheet. It's about what gets loaded where, how it's split across GPUs, and how to predict and reduce your memory overheads before it crashes your pipeline. Now first, let's understand why we should talk about model parallelism. Whether we're training massive models or deploying them in production, GPU memory constraints constantly trip us up. Also, training demands space for waits, activations, optimizer states, and even temporary buffers for computation and communication. These memory consumers quickly add up, exceeding even high-end GPU's capacity. Typically, the optimizer states consume even more memory than the model weights themselves. Most of us optimize for model size and parameters. Few of us think about the memory, and that's where the bottlenecks begin. So in this session, we learned to first estimate GPU memory requirements with simple, reliable rules of thumb. Second, leverage tensor parallelism, which splits weights across GPUs by columns or rows, particularly in the attention and MLP layers. Third, use pipeline parallelism to divide the layers across GPUs in an assembly line, while being mindful of the pipeline bubbles. 4. Explore data parallelism, where we can fit the model on a single GPU, but we split the input batch across multiple GPUs to increase throughput. 5. Understand how collectives like all-reduce and all-gather power these parallel strategies. Finally, we will understand how these techniques combine in the real world through 3D parallelism and hybrid model training. So, grab your favorite beverage, fire up your VS Code, and let's begin this journey into scalable deep learning systems. Let's start by trying to load a large model on a single GPU. So in this demo, we're using an AWS SageMaker notebook on a G6.12x large instance. This instance has 4 NVIDIA L4 GPUs with around 24 gigabytes of memory each. We can see this by executing the NVIDIA SMI command on the terminal here. So here we can see that there are 4 GPUs, each of which has around 24 gigabytes of memory, and currently there are no running processes that are consuming GPU memory, so it's all completely empty. We'll be using a few different packages today, including transformers, PyTorch, and Accelerate. We'll be showing the versions of the packages that we're using here. Let's do the imports as we need it. And let's start by trying to load the Qwen 32B model on a single GPU. So this is a typical Hugging Face API, the from pre-trained. We have executed this before. So the first time you actually try to run this, it will try to download the weights from Hugging Face itself. But here, since we've already executed it, it will read it directly from the cache. So let's try this. So we're loading the model onto the GPU device 0, which is on a single GPU. And as expected, our GPU is not large enough to hold the entire model, so we see the dreaded CUDA out of memory error. So So by the end of this masterclass, you'll not only understand why your model crashes, you'll also know how to fix it. So now let's dive in. Before we dive into parallelism strategies, let's first take 2 steps back and revisit the architecture we're working with, that is, transformers. On the left, you see a high-level view. The inputs come in after passing through an embedding layer, flow through a stack of transformer blocks, and finally the LM head to obtain the output token logits. On the right is our atomic unit, a single transformer block composed of a multi-head self-attention component with QKV projections followed by the output projection, and then a feed-forward network, 2 linear layers sandwiching an activation. Example, GELU. This structure is repeated layer after layer, and it's precisely because of this repeating, heavy architecture and huge weight tensors that transformer models quickly exceed GPU memory. Now that we've established why the model crashes and what we're actually dealing with, we're ready to explore how tensor parallelism can help by slicing the model's computation at the sub-layer level. All right, we've already seen how loading a large model on a single GPU could lead to an out-of-memory error. So how do we still work with large models? We split them across multiple GPUs. The first strategy in our toolkit is tensor parallelism, where we break down individual weight matrices across GPUs. Not entire layers, not entire blocks, just the weight matrices inside the layers. Tensor parallelism means dividing the computation of a single matrix multiplication across multiple GPUs. Instead of each GPU holding a full copy of the model, we slice up the weight matrices and distribute the computation. Let's start with a simple example. X is a 2 cross 4 matrix. That's our input. A is a 4 cross 2 matrix. That's our weight. Their product, Y, is a 2 cross 2 matrix. If we do this multiplication on a single GPU, we will compute Y equals X times A. Straightforward. But how do we do this on multiple GPUs? There are 2 main ways. 1, column parallelism, and 2, row parallelism. Let's explore both. First, let's look at column parallelism. Here's what happens. We split the weight matrix A into 2 halves by column, A1 and A2. We keep X intact. We feed the same input matrix to both GPUs. GPU 1 multiplies X with A1 and produces Y1. GPU 2 multiplies X with A2 and produces Y2. Finally, we concatenate the 2 partial results column-wise to get the full Y. So visually, you can think about it as each GPU handling a slice of the output dimension. Each GPU communicates its slice of the output to every other GPU via an all-gather operation. Column parallelism is typically used in the LM head layer of the LLM and is especially useful when working with very large vocabulary sizes. Next, let's look at row parallelism. This time, we split the weight matrix A across 2 rows into A1 and A2. But this also means that we must split the input matrix X accordingly to ensure matrix multiplication compatibility. We split X using column parallel into X1 with columns matching A1 and X2 with columns matching A2. Now GPU 1 computes X1 times A1 equals Y1 and GPU 2 computes X2 times A2 equals Y2. But now to get the final result Y, we actually have to add Y1 and Y2. This is called an all-reduce operation, where all GPUs share and sum their partial outputs. So here, each GPU is handling a slice of the overall matrix multiplication, and we need to aggregate them to get the final result. Tensor parallelism is a core part of frameworks like Megatron LM, DeepSpeed, and VLLM, which are used to scale LLMs like Qwen, Llama, and more. In fact, the original Megatron LM paper from NVIDIA was one of the first to propose these parallelism strategies. All right, we've now seen how tensor parallelism splits computations within a single layer, distributing the load smartly across GPUs using row and column strategies. But this was all on paper. Now it's time to get hands-on and see this working in code. Now, let's get back to our notebook and see tensor parallelism in action. So for demo purposes, we will create a few sample tensors that can demonstrate the matrix multiplication. So we have created 2 tensors, tensor A of shape 2 cross 4 and tensor B of shape 4 cross 6. Without any tensor parallelism, if we do the torch.matmul on this, we see the output tensor C of shape 2, 6. We'll come back to this later because these are the exact tensors we will be using to shard both for column parallel as well as row parallel. Okay, so let's start with column parallel. Recall that we shard the right hand side matrix, that is B, along its columns. Since it has 6 columns totally, we split it into 2 of 3 columns each. So we get B left of shape 4, 3 and B right of shape 4, 3. As we do in column parallelism, we do the independent matrix multiplications of A with B left and A with B right. We get C left and C right doing this process. Now, what remains for column parallel is the altogether. So when we concatenate these two matrices along dimension 1, we essentially get the same output back. So this demonstrates how we have split the computation of this matrix multiplication of A and B into 2 and then gotten the same output as before just by a simple altogether. So this operation is particularly very useful in the LM head layer of a large language model to efficiently compute the output logits. Imagine each GPU individually computing a subset of the vocabulary, and then finally we all gather the logits across all ranks before doing the final sampling. Next we can come to row parallel. Row parallel is pretty, conceptually very similar to column parallel with just a few minor changes. You can think about this as just the transpose of column parallel. So in this case, we just shard A along its rows. So we get A top and A bottom. Similarly, we compute C top and C bottom by multiplying with B. And this time we concatenate along dimension 0. We've kind of skimmed over the stepwise computation here because it's essentially the same as column parallel. Let's execute this cell, and as you can see here, we get the exact same output by sharding along row parallel as well. Things get more interesting when we do column parallel and row parallel together. Let's see what happens when we shard A using column parallel and B using row parallel simultaneously. So in this cell, we have sharded A using column parallel, split it into 2 columns each, and similarly B using row parallel with 2 rows each. We can see the 4 matrices here: A shard 1, A shard 2, B shard 1 and B shard 2. Next, we compute C shard 1 and C shard 2 using the corresponding shards of A and B. This is equivalent to the computation that will be done on each individual GPU using its respective shard of the weight. Let's look at what the output tensors look like here. Interestingly, we get 2 shards like C shard 1 and C shard 2. Both have the same shape, which is 2, 6. What is interesting here is that they're actually the same shape as the final output C, that is 2, 6. But there is an interesting pattern here in the sense that all we need to do is add these 2 matrices together to get the final expected output. This is what is done in the GPU world through an all reduce, where each GPU communicates its output to every other GPU, and it's all summed together to get the final output. Using row parallel and column parallel is especially useful in the attention and MLP layers of the transformer. Let's now focus on how tensor parallelism looks. Okay, let us now look at column parallel and row parallel in action in a transformer MLP layer. Here is the formula for the computation done within a single MLP layer. We have an input. We first do an up projection on it using a matrix multiplication. Then we apply an activation, in this case the ReLU nonlinearity. And then we take that and then multiply it with the down projection weight to get the final output. Let's define a few terms here to see what the shapes of these matrices will look like. Typically, we say S is the sequence length, H is the hidden size, and I the intermediate size. With this, we can say that the shape of the input is S, H. The down projection weight projects the hidden dimension into the intermediate dimension, and the down projection weight projects the intermediate dimension back into the hidden dimension to give us a final output which is the same shape as the input S, H. We'll create a few small tensors here for demonstration. So let's say we have a sequence length of 2, a hidden size of 4, and an intermediate size of 6. This makes it easy for us to see the outputs here in the demo. So let's create these tensors and view them. We have our input tensor, our up projection weight tensor, and our down projection weight tensor of shapes 2, 4, 4, 6, and 6, 4 respectively. Let's first compute the expected output of the MLP layer without any tensor parallelism first. Okay, so we have our output here of shape 2, 4. Let's now apply column and row parallelism. One interesting difference between what we did in the previous section and what we're doing now is that there's actually a non-linearity here, right? In the previous section, we were multiplying just A and B, and we were sharding A by column parallel and B by row parallel. The difference here is we have 3 matrices. We actually have input, the up projection weight, and the down projection weight. Moreover, we have an additional non-linearity here. Despite this, we are still able to do column and row parallel successfully, and that's what we will demonstrate now. So let's shard the up projection weight and the down projection weight using column and row parallel respectively. So on GPU 0, we will have 1/2 of the up projection weight sharded by column parallel and 1/2 of the down projection weight sharded by row parallel. This is what the weight tensors on GPU 0 will look like. Similarly for GPU 1, it will contain the other half of the weight tensors that and together they comprise the entire weight tensors. Now let's see what happens when each GPU computes the output using their own shadow weights. By computing output, we mean that the entire MLP operation is done here. So notice that we are first doing the up projection on the input with just the shadow weights on GPU 0, then applying the activation, the ReLU, and then we're using the down projection to get the output of GPU 0. This is the output we obtained. Let's do the same thing on GPU 1. Okay, so now we have 2 tensors of shape 2, 4. How does this relate to our final output? Recall that our final output is expected to be this particular tensor. Can you see the pattern here? 44 plus 600 equals 644. 900 minus 121 is 779, and so on. So this essentially means that if we all reduce our outputs across GPUs, we will get the final expected output. This trick of sharding the weights using tensor parallel holds true for any number of shards. We've demonstrated here using 2 shards, but generally you can use 4, 8, whatever, depending on how many GPUs you want to shard your weight matrices into. The number of shards is called the tensor parallel degree of your parallelism configuration. Next up, we'll shift gears to a different strategy, pipeline parallelism, and explore how to turn your transformer into an assembly line. All right, now that we've seen how to break a single matrix or layer across GPUs using tensor parallelism, what if we could treat entire layers as chunks and send them off to different GPUs, kind of like parts of a manufacturing process? That is the promise of pipeline parallelism, and it is a key part of what makes training ultra-deep models like GPT or Llama feasible at scale. Tensor parallelism works wonderfully for individual matrix multiplications, but as models grow deeper, not just wider, even sharding the matrices may not be enough. Let's say you have a 96-layer transformer model, and you're trying to run on a node with 4 GPUs. Even if you try to fit all layers on every GPU, even with tensor sharding, the memory just may not cut it. What we need instead is a layer-wise split, where each GPU handles only a few consecutive layers. Think of your model as a relay race. Each GPU holds a baton for part of the race, a chunk of consecutive layers. Once it finishes its leg, it passes the baton to the next GPU. More formally, the model is split into multiple pipeline stages. Each stage contains a subset of the transformer layers, and these stages are assigned to different GPUs. Let's say you've got a 12-layer transformer and 4 GPUs. We can split this into 3 layers per stage. GPU 0 contains the input embedding and the layers 1 to 3. GPU 1 contains layers 4 to 6, GPU 2 contains 7 to 9, and GPU 3 contains 10 to 12, followed by the LM head. Let's look at the diagram you see on the screen now. Each horizontal line represents one GPU, 0 through 3. Each colored box is a task. F0, F1, F2, F3 are the forward passes of each stage, whereas B3, B2, B1, and B0 are the backward passes. We also have the parameter update happening in each GPU. So what happens here? GPU 0 starts the processing by applying layers 1 through 3 on the input. Once it's done, it passes the activations to GPU 1, which does its own job, and so on and so forth until GPU 3 completes the full processing of the transformer layers. Once the forward pass is complete, the backward pass can begin, this time in reverse, starting from GPU 3 computing gradients for all its parameters. GPU 2 then picks up its share, and so on and so forth until the gradients are back propagated to GPU 0. This allows us to keep each GPU focused on just a few layers and reduce the per device memory footprint. In the process, we are also increasing the model capacity per node. But wait, what about efficiency? Here is where the trade-offs begin. We've seen how pipeline parallelism splits the model into stages across GPUs. Stage 0 on GPU 0, stage 1 on GPU 1, and so on. Let's now zoom in on something less obvious, but incredibly important. Pipeline bubbles. Here's a quick question. If only GPU 0 starts processing the input, what are GPUs 1, 2, and 3 doing in the meantime? Exactly nothing. They're idle. This idle time, where some GPUs are waiting for data from earlier stages, is what we call a pipeline bubble. This sequential data dependence is a source of major inefficiency. Let's break this down using the diagram on screen now. The top part of the image shows the model processing the data as a single batch. On GPU 0, we see the forward pass F0 starting immediately, but GPU 1 can't start its job until F0 finishes and sends its activations. Same holds for GPUs 2 and 3. The same thing holds in the backward pass as well. It starts from GPU 3, then goes to GPU 2 and 1, and so on. The result of this? A lot of waiting, meaning that the GPUs are severely underutilized. Most of the time, they're simply idling, causing this pipeline bubble. Let's now look at the bottom part of the image. Here's where the magic of microbatching kicks in. Instead of feeding in one big batch and waiting for it to travel through the entire pipeline, we split the batch into multiple micro batches, F00, F01, and so on. This means that both the forward and backward passes are staggered across multiple subsets of the input data. The result? Each GPU is working on some part of a microbatch at almost all times. The pipeline bubble is now much smaller than before. You can see this in the lower diagram that no GPU is sitting idle for too long. Microbatching has helped minimize the bubble to a good extent and thereby improve hardware utilization. Now let's pause and compare the two. Tensor parallelism splits individual matrix operations, whereas pipeline parallelism splits the entire transformer layers across multiple devices. Pipeline parallelism is more memory efficient, but often less GPU efficient if the pipeline is not deep or well batched. Unlike tensor parallelism, where we had to synchronize activations in every single layer, pipeline parallelism only needs to send data between layers and much less frequently. So when should you use pipeline parallelism? It's often a good idea when your model is quite deep, example 24 layers or more, where memory is the bottleneck and you can't afford full replication. When your hardware has slow interconnect and you want fewer synchronizations. But it's also a good idea to avoid it when you have small batch sizes and you need very low latency. Often, it is preferred during training and not during inference. Pipeline parallelism is not as bandwidth intensive as tensor parallelism, but as with everything, it comes with its own trade-offs. The best choice always depends on the model architecture, hardware topology, and latency tolerances. Let's now jump back into the code to see how tensor and pipeline parallelism can be used to load the large Qwen 32B models across multiple GPUs. Coming back to our notebook, we see part 3 and 4, which are for tensor and pipeline parallelism respectively. So this part of the code actually needs to be executed on the terminal and not directly in the notebook. For tensor parallel, we'll be executing this command, which is torch run with number of processes per node equal to 4, This is actually equal to the number of GPUs we have on our current instance. We'll be executing tensorparallel.py. Let's take a quick look at the code that's being executed inside this file. The first thing we do here is to initialize the process group. This is a torch distributed specific thing that we need not focus on at the moment. The next thing we do is a very familiar looking from pre-trained call from Hugging Face API. We specify the name of the model as the Qwen332B model. We want to load it in the bfloat16 data type, and we specify a cached dir where the model checkpoint will be downloaded the first time you execute it. The crucial part here is actually specifying the TP plan. So this specifies how the model should use tensor parallelism. Here we specify it to auto to tell Hugging Face that you can choose whatever strategy you feel is best. We will actually be seeing this, printing and seeing this plan later when we execute the model. So we'll come back to this. The rest of the code is actually very, very simple. We just load the tokenizer, we define an input prompt, and we simply run the model that we loaded with TP. This will execute tensor parallel inference. And then finally, we'll display the output here. The prompt here is to ask the model why it finds tensor parallelism fascinating. So let's see what Qwen has to say a little bit later. Okay, so let's try executing this command now. We go to our terminal and we execute this command. Let's see what happens first. Okay, our checkpoint is first getting loaded. Note that this will get evenly sharded across all GPUs, and we'll see that in action now. When we can view the GPU utilization, we can see that around 18 gigabytes of memory is being used on each GPU out of the 23. So the torch run command has actually made us use all the GPUs present on our instance and evenly shards the memory utilization across all of them. Okay, so our script has executed now, and let's look at what it gave as output. First, let's focus on the TP plan. Here we can see how the Hugging Face chooses to shard each individual layer of the model. We can see that in the attention layer, the Q, K, and V projections are sharded using column parallel. And the output projection, the O projection, is sharded using row parallel. It's an interesting exercise for you to work out why this works on your own, because attention, obviously, is slightly more complex than the simple MLP case we discussed in today's class. Then we can come to the MLP itself. This is exactly the same as what we covered earlier, and we have our gate projection, up projection, and down projection, where the first two are column parallel and the next one is row parallel. This is just a repeat, so we can kind of ignore what is happening here. We've covered how every individual weight matrix gets sharded here. Note that neither the vocabulary nor the LM head is being sharded here, but if we want to, we can specify that. It's an interesting thing to try on your own. Okay, and let's see what the model has to say about tensor parallelism. Okay, so it finds it fascinating because it enabled efficient distribution of large models across multiple devices with optimized computation and memory usage. Perfect. Okay, now we have seen tensor parallelism in action. Next, let's come to pipeline parallelism and try to load the exact same model as before. For this, we'll be executing a very simple Python command. Let's first take a look at this pipeline parallel.py script again. This looks very, very similar to the tensor parallel script that we saw before. The only change here is that we specify device map equal to auto. Recall that we specified TP plan equal to auto here. If we specify device map equal to auto, then Hugging Face automatically partitions the model using pipeline parallelism. We have a way to view how the model is sharded by Hugging Face here, which we will see when we execute the model. And the rest of the code is pretty much the same. We are just executing inference on a single prompt using this pipeline parallel model. Okay, now let's look at executing this model. Similar as before, we are loading the model checkpoint shards first. Great. Now that the model is loaded, let's look at what the memory utilization looks like. What's interesting to note here is that the memory utilization is no longer even across all GPUs. Note that only around 14.7 GB is used on the first and last GPUs, whereas the middle GPUs are consuming around 17 gigabytes. Can you guess why this is happening? We'll look into this a little bit more. But this is interesting because for Tensor Parallel, you can see that the model is pretty much sharded equally across all ranks. Whereas for Pipeline Parallel, there is a slight imbalance in the way this is happening. This is why this is happening. This is the Pipeline Parallel plan that was printed out. For each intermediate layer of the model, we can see the GPU that it was partitioned into. So we have 0, 1, 2, and 3, because we have 4 GPUs. Let's count how many layers go on each GPU. So the input embedding layer is on GPU 0, and then all layers up to layer 13 are on GPU 0. So 0 through 13 are on GPU 0, which means there are 14 transformer layers that have been assigned to GPU 0. Let's look at how many were assigned to GPU 1 now. So from 14 through 31, which means there were 18 layers that were assigned to GPU 1. Similarly, there are 18 layers assigned to GPU 2, layers from 32 through 49. And then finally on GPU 3, we have layers 50 through 63, which is 14 layers, followed by the LM head. And then we can also consider the output normalization, rotary embedding, and so on. So this is the cause of the imbalance. Does this make sense now that the GPU 1 and GPU 2 have the same utilization? This is because both of them had the same number of transformer layers, whereas 1 and 3 had fewer number of transformer blocks, but then they also had the input and output embedding respectively. All right, our inference is complete. Let's see what Quen has to say. Okay, so it finds PP fascinating because it optimizes your resource utilization by overlapping computation and communication, significantly improving the efficiency and throughput of the distributed systems. We have seen how to successfully load and run the Quen 32B model across multiple GPUs using two different model parallelism strategies. First, we saw TP, and then we saw PP. Let's now take a short detour from model parallelism and talk about a simpler but very commonly used method, data parallelism. While our focus for this talk is model parallelism, understanding data parallelism gives valuable perspective and helps frame more advanced methods. Data parallelism in its simplest sense is used when your model is small enough to fit on a single GPU device, but you're unable to run with a large batch of inputs. That is, you need to increase model throughput. In this case, you're not actually bottlenecked by the model weights themselves, but by the activation memory consumed by the inputs passing through the model. In this case, we can adopt a very simple strategy. Simply replicate the model weights across multiple GPUs, but split the input batch into multiple shards. For inference, each GPU can independently process its own share of inputs, thereby enabling a much greater throughput than before. It gets slightly more complex during training. First, each GPU computes the forward and backward passes on its own share of inputs. Then, there is a gradient synchronization step through an all-reduce operation, thereby ensuring that the parameter updates are identical across all model copies. Data parallelism is ubiquitously used across both model training and inference, and often in conjunction with model parallelism techniques. We've now explored the major strategies that help us scale large language models across hardware boundaries: Tensor Parallelism, Pipeline Parallelism, and Data Parallelism. But real-world models like GPT, Claude, and Quen don't just pick one, they combine them. And that brings us to our final strategy, 3D parallelism. By now you understand that Tensor Parallelism breaks matrix multiplications within a single layer across GPUs. Pipeline parallelism splits entire layers across GPUs in a sequential, assembly-like fashion. Data parallelism operates on full model replicas, but processes multiple input batches in parallel. Each approach has its trade-offs. TP has significant inter-GPU communication needs. PP causes suboptimal compute utilization due to pipeline bubbles. DP hits memory walls if models grow too large. So when training a massive LLM, when you're dealing with billions of parameters, thousands of GPUs, and tight training deadlines, we need to combine all three of these to balance memory, compute, and communication. This is called 3D parallelism. We can visualize this as a cube, as shown on the screen. Along the depth axis, front to back, you have model or tensor parallelism via tensor sharding. Along the horizontal axis, you have pipeline parallelism with layers spread across stages. And along the vertical axis, you have data parallelism, where each group trains on a different mini-batch and synchronizes gradients. Each technique is orthogonal to the other and can be combined with one another as needed. This kind of 3D parallel setup ensures that no single GPU needs to hold the full model, memory usage is tightly controlled, and that the workload is spread evenly across compute nodes. In addition, we also minimize the communication overhead by compartmentalizing and optimizing it. Let's say we're using 32 GPUs for a 70B model like Llama 2. One of the ways to configure 3D parallel in this case would be to use two-way DP for better gradient throughput, four-way PP for splitting the model into 4 stages, and a four-way TP, where each weight tensor is sharded into 4. That is, 2 into 4 into 4 equal to 32 GPUs in total. So why this kind of arrangement? Tensor parallel requires fast intra-node bandwidth, so we like to keep TP within a single node. Pipeline and data parallel are less communication heavy, so they can be used across nodes. This kind of arrangement allows scaling efficiently across multiple nodes in a data center. While it may look trivial in its design, 3D parallelism is not at all trivial to implement. You need to think about synchronizing activations and gradients across TP shards inside a single PP stage, coordinate forward and backward activation flow across PP stages, handle data partitioning and aggregation across DP groups, and efficiency of collectives such as nickels, all gather, and all reduce to minimize the communication overhead. Frameworks like DeepSpeed, Megatron LM, and Hugging Face help abstract away these details, but understanding them helps optimize the topology and achieve best performance. Meta's Llama models, OpenAI's GPT-4, and Google's Palm all use variants of this architecture for training their models, often with additional bells and whistles, such as Zero for optimizer state sharding, activation checkpointing, and mixed precision training. 3D parallelism is like designing a metro system. Some tracks go north-south, some go east-west, and some tunnels below the ground. Working together, they move billions of tokens smoothly, efficiently, and at scale. Let's now take a breath and reflect on how far we've come. We started with a problem. Your model doesn't fit on a single GPU. This is a frustrating but real scenario. And it opened the door to a deeper question. How do large-scale models like GPT or Llama run across hundreds or even thousands of GPUs efficiently? We learned that fitting and scaling large models means understanding what consumes GPU memory: parameters, activations, optimizer states, and communication buffers. And with that mental model, we stepped into the world of model parallelism. Throughout, we stressed production realism, why TP is communication heavy and best within nodes, how PP trades memory for utilization and introduces pipeline bubbles, when DP works well for increasing throughput during training and inference. These aren't just theoretical choices. They're what shape model throughput in inference clusters, cost per token during training, and energy and memory efficiency at massive scale. If this session sparked your curiosity, here are some directions to explore next. You can start by reading relevant research papers, such as the Megatron LM paper by NVIDIA, Zero by Microsoft, which talks about optimizing memory for large-scale training, and this paper from NVIDIA and Stanford, which talks about how cluster-level training can be performed efficiently. Next, you can get hands-on yourself and experiment with these techniques using various open-source libraries. Try loading and sharding Qwen 7b or Llama 3 on multiple GPUs using Hugging Face or DeepSpeed APIs, as we demonstrated in the demo. Play with different models, workloads, and parallelism strategies, and explore the trade-offs between memory utilization and speed. Scaling isn't just about throwing hardware at the problem. It's about knowing how to divide the workload efficiently as well. And that's what today was really about. Giving you the mental models, the hands-on strategies, and design patterns that power modern LLM infrastructure. I'm Goutham, and this was an NIAT masterclass on scaling LLMs with model parallelism. Thank you for learning with us. And as always, keep learning, keep building.